Okay, guys, we're going to start again. So the second session is about online learning. And the first talk is a paper from Dan Garber from Terion, but he cannot make it today, unfortunately. So it's Fear Levy from ETHZ that is going to give this talk.
Okay, thanks. Hi all. So let's start with the setting. So in this online PCA setting, you can think of this setting as a sequential game between two players, a decision maker and an adversary. So in each round of this game, a decision maker chooses a unit vector WT in RD, and then the adversary reveals his choice for a vector XT from the ball of radius R, and then the decision maker incurs a loss, which we call the projection loss, and this is just the square of the difference between XT and the projection of XT to the linear subspace spanned by WT. Okay, so as is standard in online learning, our goal is to minimize the regret, and the regret here is defined as the cumulative loss of the decision maker minus the cumulative loss of the best point in hindsight. And quite nicely, you can actually write this expression of the regret as the second expression that you see below. And here you can see that that's an online maximization problem. And what you can see is that the decision maker tries to compete against the largest eigenvalue of the data matrix in hindsight. Okay, that's why it's called the online PCA problem. So this problem is actually not convex, or in the maximization formulation, it's not concave. So unfortunately, we cannot apply standard online convex optimization tools. And specifically, we do not have any guarantees for the online gradient ascent algorithm for this problem. Okay, but as is well known, you can actually relax or convexify this problem, and the relaxation goes as follows. Instead of allowing the decision maker to choose vectors, we allow it to choose matrices, this capital WTs that you see here, and these matrices are positive semi-definite, and their trace is equal to 1. So another part of the relaxation is, instead of looking at the original loss functions, or actually reward functions, we are defining reward functions which are actually linear in W, in this matrix W. So now the relaxation that you see on the right-hand side is actually an online concave maximization problem, or actually an online linear maximization problem, and therefore we can apply standard tools to provide guarantees for this relaxation. So quite nicely, if we can solve the relaxed problem, we actually have a solution for the original problem, and this is since each of these matrices, WTs, induces a distribution over unit vectors, okay? Which means that the equality that you see here applies, and this actually means that if we have regret guarantees for the relaxed problem, this actually translates to regret guarantees for the original problem, but now the guarantees are only in expectation. Okay, so if you look at the relaxed problem, the natural algorithm that we can think of is just an online gradient ascent algorithm over this relaxation. So for this relaxation, as we've said, we can apply standard analysis to show that it actually enjoys sublinear regret, but this comes with a cost. And the cost is that now, since we are considering matrices, then this requires a memory of O of D square. And since we are doing online projected gradient ascent, then we need to do, since this set of positive semi-definite trace 1 matrices, we have to project into it. This projection requires an SVD decomposition, and this takes d3, d cubed runtime per iteration. Okay, so now let's go back to the original non-convex formulation and look at the non-convex online gradient ascent for this problem. That's what you see here. We have an update step and a projection step. And actually, this algorithm has guarantees in the offline setting where the data matrix is given in advance, and it also has guarantees in the stochastic settings where the XTs are coming from some unknown distribution D. And the question that Dan asks in this work is, can we prove anything about this online gradient ascent algorithm also in the adversarial setting? So the answer is yes. So what Dan actually considers is an intermediate model between stochastic and fully adversarial setting. So what we assume here is that the XTs are having two components, QT, which is a stochastic IID component, and VT, which is an adversarial component. And we assume that the norms of these VTs and QTs are bounded. And we also assume that the expectation of Q is 0. So both of these assumptions are standard. The new assumption that Dan makes here is that if you look at the covariance matrix of the stochastic ingredient, then the eigengap of this covariance matrix is larger than something, is large enough. And this additional assumption actually means that if we look at the W star, the best in hindsight, it actually should be close to X, which is the top eigenvalue of the covariance matrix of the stochastic ingredient. Okay, so this is a simplifying assumption. Okay, this means that X has a correlation with the best in hindsight, but this assumption is not trivial, since if you look at X, the leading eigenvector of Q, it may incur a linear regret. Okay, so the guarantees in this work of Dan says that if you have a warm start, meaning that if you have a vector, if you start at a vector W1, which has a high enough correlation with X, then you apply this non-convex online gradient ascent algorithm, you actually ensure a square root of T regret. And then, as an additional contribution, what Dan shows is that under additional assumptions regarding the eigengap of this matrix Q, Dan shows that you can find such a warm start W1 efficiently. Okay, so the idea of the proof is the following. First, we consider somehow an intermediate algorithm. The algorithm that you see here is somehow an intermediate algorithm between the non-convex online gradient ascent and the online gradient ascent for the relaxed problem. And the observation of Dan is that if WT plus 1 is rank 1, then this algorithm is actually the standard online gradient ascent over the relaxed problem. And Dan actually shows that this is the case. This WT plus 1 are of rank 1. And then what we show, what Dan shows is actually that the online gradient ascent, the non-convex online gradient ascent algorithm is a good enough approximation of this hybrid online gradient ascent rule that we have on the top of the slide. Okay, so the idea is the following. If you can show that, so now I'll tell you about the idea of, So now I'll show you why does this rank 1 condition holds. So what Dan shows that if the correlation between WT and X is high enough, then with high probability, WT plus 1 is rank 1. And then what Dan shows iteratively that the correlation between WT plus 1 and X cannot go down below a certain level. Okay, and that's basically the idea of the proof. And that's it. And Dan is looking for a postdoc. Don't hesitate to contact him.
You have a nice question for Kfir, but it's not Dan.
It is well.
Do you know if delta must be known before the algorithm?
Sorry?
Parameter delta. Does it have to be, does the algorithm knows it in advance?
I think it does. I think it should know it.
Okay. Thanks again for. Okay. The second speaker is Alon Gonen from Princeton, and he's going to speak about learning in non-convex game.
Thank you. So I will talk about learning in non-convex games using an optimization oracle. This is joint work with Naman Agarwal and Elad Khazan. So as we know, many important machine learning optimization tasks are non-convex, and non-convex optimization is hard in general. So gradient great effort has been made to identify useful distribution geometric condition under which we can minimize learning, non-convex learning problems. For example, no spurious minima, strict saddle, etc. And many results in this spirit have been shown in the recent years with application to deep learning and low-rank metrics recovery. And most of these results apply in the offline setting. And as we know, learning usually introduce another challenge where the learner has only stochastic or even online adversarial